Hello everyone. We're going to, in section 6.2, we're going to talk about the inverse functions. Now you are familiar with inverse functions, hopefully. Typically, inverse functions are taken up in an algebra class, second algebra class, and they're also the subject of a pre-calculus course. So you have familiarity with this concept. We're interested in the calculus of inverse function, if you will, at this point. So briefly, we're going to talk about a theorem that relates a function, a derivative that is, of a function to its inverse. But before we go there, we're just going to cover some preliminary ideas and then definitions. So first of all, the definition of inverse function. If you recall, the inverse function is obtained when we swap out or interchange or exchange the xy coordinates of an equation or a relation in that matter. So in definition 1 that you see here, inverse function, a function g is the inverse of a function f if the composition of f of g of x is x. This is another way to describe the inverse function. Of course, in algebra classes, this becomes a property of a function and its inverse. In terms of the composition of f of g of x would give you x. Now what's important in this definition is that x must be in domain of g, so this value here. It is only x when x is in the domain of g. Another way to think about it is if x is in the range of the inverse, would be in the range of f. Because remember, anytime we switch or swap the xy in order to obtain the inverse, we switch the roles of the domain and the range of a function as well. So what used to be domain becomes range, what used to be range becomes domain. And this is evident from the graph that you see on the right side. So what you see on the right side here, this is the graph of a function, and this would be the graph of its inverse. Now this idea of switching or swapping the x and the y causes the reflection that you see, or I should say the symmetry, not the reflection, but the symmetry that you see about the line y equal x. Okay, and if you note where AB is a point on the graph of a function, you swap the A and the B, and BA will be on the graph of the inverse function. So this is how typically the inverse function is found. When it comes to the composition g of f of x, that should also equal to x, and that would be the idea here. That would be the composition. So remember, the order of composition, in other words, doesn't matter. The order of composition, whether it's f of g of x or g of f of x, either way you get x. You got to be, again, mindful, very important, that x is in the domain of g here and x is in the domain of f, the inside function. And that becomes very important when it comes to trig functions, because when we restrict the domain of trig functions, then the composition of f of g of x equal x only happens if we restrict the functions for trig functions. That's something we'll talk about later on when we talk about the derivative and integral of inverse trig functions. Okay, and let's see. The next definition is that of a one-to-one function. A one-to-one function is one so that anytime the x's are different, we're looking at two functions. We're looking at one function, two different values on a function. So to clarify what I mean here is the following. Let's say I'm making up this parabola, the basic parabola here. Okay, this is x squared. Now, anytime x1, x2 are different, the function values must be different. Okay, so in here, suppose I have a point 2, and 2 squared is 4. So 2, 4 is on the graph of this function, and -2 and 4 is also on the graph of the function. So notice for different x values here, 2 is not equal to -2, so it kind of looks like this construct. Okay, whenever the x's are different. In my example of x squared, notice the y's are the same, they're both 4. So the y values are not different. Therefore, this function, which is a basic parabola, that's not a one-to-one function. So I can say that 2 is different from -2. Maybe, however, f at 2 equals f at -2. They should be different, but they're not. So that would imply that this function, that f of x, is not 1 hyphen 1. It's not 1 minus 1, it's hyphen 1 hyphen. So it's a 1-to-1. It is not 1-to-1. That's what my f of x is. So that's the definition of one-to-one function. And sometimes, and we'll see, in order to show that two functions are, or a function is not one-to-one, all it takes is find, look, I have an example where you get two different x values, but you get the same y values. Okay, now your two different x values could be x and a negative of x, for example, just like I have here. See, I have x is 2, negative of x is -2. I'll show you how to do this in an exercise, and what I mean by showing the function is not a one-to-one. One thing that's noteworthy is the following. For example, suppose I have this half circle. You probably all are familiar with the horizontal line test, in that if you draw a horizontal line and crosses the graph of a function at two different points, the function is not one-to-one. So again, here an example of a function that's not one-to-one, a half circle or even a full circle. And the reason for that is, if you can see, let's say I have x1, x2, I have two different x values. However, they have the same ordinate or the same y value, right? The y's are the same. So I can say that in this case, x1 is different from x2, but again, f at x1 is indeed equal to f at x2. So that would imply that the function is not one-to-one, and that's commonly known as the horizontal line test. And in the exercises, we'll see they ask us to show the function is not one-to-one. We can do it both ways, either by showing the very definition fails or using a graph. Next, we got these theorems. Theorem 1, existence of an inverse function. A function has an inverse if and only if it is a one-to-one function. Okay, so, and that's the prerequisite. If a function is not one-to-one, it will not have an inverse. And you can kind of see that here with my made-up example too. If I want to find the inverse function here, remember, we're going to switch the x and the y. So I get 4, 2. That's the inverse corresponding to that point. The inverse of -2, 4 becomes 4, -2, right? Now, if you look at this ordered pair has the same x values. Well, if we have a relation means a set with ordered pairs. So if I have, let's say, a set, and its members are, for example, 4, 2, 4, -2, then this relation cannot be a function. Cannot be a function. The reason, because it has the same first components, namely same x's. So therefore, this is not a function. That relation is not a function. So you kind of see why this makes sense. The function must be one-to-one in order for it to have an inverse, so that we avoid the situation here. Okay, and that's that. Now the second theorem talks about the continuity and differentiability of inverse functions. So suppose we have a one-to-one function that has an inverse. Remember, by theorem 1, this would make sense. The presupposition of the theorem holds, or the hypothesis of the theorem holds. In number 1, item 1, if the function is continuous on its domain, then its inverse is continuous on its domain. Okay. And if f is differentiable at c, then f prime at c is 0. Okay, if the function is differentiable at c at a point and its derivative is 0, then f inverse is also differentiable at f at c. Now we're showing you these theorems, by the way, without proving them. Okay, the proof is in the book if you're interested. All right. So again, theorem 2 had to do with continuity and differentiability of inverse function. That is good. So we know that the inverse function is continuous and the inverse function is differentiable, provided the function that the inverse stems from is continuous, and the function again that initiates or originates the inverse function is also differentiable. So continuous one-to-one functions have continuous inverses. Differentiable one-to-one functions have differentiable functions, right? Inverse, their inverse will be differentiable at that point. Okay, this is differentiability at a point at C. Okay. Now, theorem 3 is an interesting theorem. The theorem 3 reads that the derivative, it gives us the derivative of an inverse function. So in this theorem, we have let f be differentiable on its domain and have an inverse, okay, which the book calls it g. Okay, then the derivative of g is given by what you're looking at. Okay, so that's what the theorem tells us. So this theorem builds a connection between derivative of the inverse, remember g prime is inverse, and f prime is the original function. Okay, so a function and its inverse, that's how they are related to each other. Okay, and of course provided the denominator is not 0. Okay, and we will see example of this in a moment. In fact, let me give you an illustration of an example for theorem 3, okay, to see how this works. So an example of the illustration of this theorem. It's not a proof, it's an illustration, an example of the theorem, what it says. So I'm going to let my f of x, which we call it y, would be x cubed. Okay. Now, if I want to find the inverse, we swap, right? We're going to swap the x and the y. So x is equal to y cubed, and solve. Remember, the two-step process for finding the inverse is the swap and solve. So that would be cube root of x. And this is what we call g of x in here. So g is the inverse, right? This is f inverse x. One thing I had it, but I didn't mention. Please be careful when you use the inverse notation. Support choice, but then it's been there forever. Every math textbooks uses it, and science textbooks. The superscript -1 is just that. It's a superscript. So it's not. It doesn't have a numerical value. So it's not a -1 on the number line. Okay, that's not what that is. That's just a notation. So the inverse, so f inverse of x, does not equal to 1 over f of x. That's the point we want to make, and that's what it says. Do not confuse the inverse with f of x to -1. The -1 here, this is actually an exponent, right? So it has a numerical value. -1 could be 2, 3, 4, 0, whatever. So it happens to be -1. This one seems like -1, but it's not. That's why I just call it a superscript. That's what that is. Think of it as a superscript, so we don't assign a numerical value to it. Okay, so let's take a look at this one. Therefore, I want to find the inverse, and I did. Now, let's say I want to find the derivative of the inverse directly. That would be g prime x. So g prime x is going to be 1/3 x to negative 2/3, right? That's the derivative of cube root of x. And I can write this as 1/3 and then square or cube root of x squared. And there you have it. So notice that's not using the theorem, that's just straight using the explicit form of the inverse. So now let's take a look at the derivative of the original function, 3x squared. Of course, they're different. They're two different functions. The function and its inverse are totally different. Now, let's take a look at this theorem. According to this theorem, g prime of x, now I'm looking at that expression, it could be found this way. I can use it as 1/f prime evaluated at g of x. Okay, now this is f prime, so that's what I'm going to use. That's 3 and evaluated at g of x. Okay, so and what is g of x? Remember, g of x is the inverse, right? The inverse, I'm sorry, g of x is not the inverse, g prime x is, I was right, sorry. G of x is the inverse, yes, g of x is the inverse. So that would be cube root of x. So that's 3 times cube root of x. Okay, and f prime g of x, and then that would be squared, right? Because f prime is 3x squared, so it's going to be 3g of x. Oh, actually, there's a squared here. That's what was missing. It's throwing me off there. Okay, and now you have it. Okay, so from here to here, I use 3x squared. Instead of x, I have g of x. That's what the evaluation point is. And there you go. Check this out. These are the same, aren't they? These are exactly the same. Okay, so so we can evaluate points on the inverse or derivative, slope of a tangent on the inverse, using actually the original function. We don't even have to find the inverse a lot of times if we want to evaluate at a point. We'll see example of this in a moment, and it will clarify what I'm trying to get at. Okay, so hopefully this clarifies what this theorem is about. And that's as far as the calculus of it goes for us for inverse functions. So remember, a function that is one-to-one and continuous, so is its inverse. A function that is one-to-one and is differentiable at point C, where the slope of a tangent at C is 0, is also differentiable at C. Okay. Now, in this segment, we're going to look at those circled exercises. So let's begin with exercise number 4. Okay, in exercise number 4, show the function f and g are inverses of each other by verifying f of g of x is x and g of f of x is x. Okay, so in numbers 4 and 6, we don't actually have to find them. They're given to us. So let's take a look at number 4. In number 4, f of x is x squared plus 1. And notice that's a parabola, right? And a parabola, I just showed in my example, that's not a one-to-one function, so it doesn't have an inverse. And what the authors do is they actually restrict the domain to just negative numbers. Over negative domain, the function becomes one-to-one because we're looking at the left branch of a parabola, not the whole parabola, but only the left side of it. And g of x is negative root x minus 1. Okay, so let's do the composition. And we want to do f of g of x first of all. So f of g of x, that's when you plug in negative of the square root of x minus 1. True. And that means you plug in for x a negative square root of x minus 1, then get squared plus 1. Right, that's the composition. I plugged it into f. And when you square the parentheses here, we're going to lose the negative sign. This becomes positive, right? The negative outside becomes positive. We're going to lose the radical sign and plus 1, and we get just x, right? So the composition yields x. Now if I change the composition to g of f of x, that would be g of, this time f of x is x squared plus 1. We're going to plug in x squared plus 1 into g function, and that's going to be x squared plus 1. That's when we plug it into here. And then minus 1, negative 1. The two 1 and negative 1 are opposite. They add to 0. And again, that's going to be a negative. We were given that's a negative. Okay. And then we have square root of x squared. Now you got to be careful here. Notice the domain of the function, right? The domain of the function, inside function, is negative. Okay, and from this we get g of f of x is equal to negative of negative x. That's since x is less than or equal 0. Again, square root of x squared becomes negative of x, provided x is negative. And the double negative makes it positive, and there you have it. So we just show the composition in both ways. F of g and g of f are both x. Okay. And that is the answer to number 4. In number 6, we have a fraction, a rational function, if you will. F of x is equal to 1 plus x over 1 minus x. And the g of x, its inverse, is given by x minus 1 over x plus 1. Remember, in this book, they use g for the inverse. Okay. So, this time, I'm going to do again f of g of x. So that means f evaluated at x minus 1 over x plus 1. That's my g of x. That would equal 2. Now we're going to plug in, okay, into this function. I have 1 plus x, but then x is x minus 1 over x plus 1. And then we have 1 minus x, which is x minus 1 over x plus 1. So we do have a complex fraction, don't we? And remember, complex fraction is when you have a fraction divided by possibly another fraction. Now, the best way to handle a complex fraction to where we turn it into an ordinary fraction is to multiply the top and the bottom by the LCD, in this case x plus 1. If we do that, we can get rid of complexity within one step. So I'm going to distribute in the bottom. I get x plus 1 minus x minus 1. Distribute the top. We get x plus 1 plus x minus 1, right? Now let's combine like terms. In the numerator, I'm going to get 2x. In the denominator, this is going to be, let's see. Yeah, it's going to be x minus x is 0. Yeah, those are opposites, add to 0, and double negative on 1 makes positive 1. 1 plus 1 is 2. Okay, and the 2's divide out or cross out, and you get there, and you get x. So we show the composition is x. Now this is true provided x is in the domain of g of x, right? In other words, this is true provided x doesn't equal negative 1. So keep that in mind. We have to be in the domain, okay, of the inside function, which would be the same as being in the range of the outside function. Now let's do g of f of x. Okay, so g of f of x is now g evaluated at f of x, which is 1 plus x over 1 minus x. And this will give me, let's see, g of x. Now I'm plugging into g function. So that's going to make it x. So I'm going to replace it by 1 plus x over 1 minus x. In the denominator, 1 plus x over 1 minus x, right? So that's x minus 1. In the bottom, we have x plus 1. And like the one above, like the one that we did just now for the f of g of x, I'm going to multiply top bottom by the LCD to get rid of the complex fraction. The LCD now is 1 minus x. Okay, and there we have it. And that will equal to, now I'm going to distribute from the right. Again, so first we're going to get 1 plus x minus 1. Distribute from the right, we get 1 plus x plus 1. All right? And, oh, actually I get 1, I'm doing the bottom, right? So distribute it here, we get 1 plus x, and distribute from the right, we get 1 minus x. Sorry. That's the binomial times 1 gives you the binomial. In the numerator, the same thing. I distributed to the fraction, I got 1 plus x. Distribute to 1, I get negative 1 plus x. Sorry, I dropped those out. Good thing I caught them. So again, in the numerator, we have 2x, and in the denominator, we have 2. The result is x. This time, x must be inside the domain of the function f of x. And domain of f of x is everything but 1. So x cannot be 1. You see how that works? So it's not just f of g of x is x, g of f of x is x, regardless of the domains. Gotta be careful here. You see that? Alright, so there's the answer to exercise number 6. Let's take a look at the others. For these other ones, I'm just gonna write them down so I don't have to scroll up and down. Some find that annoying. So just let me pause and write these down. Okay, so here are the 2 exercises we're going to do next. In number 14 and 18, we want to show whether the function is 1-to-1. Now, again, a lot of people use the graph and they do the horizontal line test. In order to show something does not possess an attribute, is to come up with a counterexample. Okay, so for example, in this case, if you want to show that these are, let's say this is not 1-to-1. If I want to show that it's not 1-to-1, then I can just find by inspection, I'm going to let, in number 14, let x be 0. And f of x would be negative 0 squared plus 2 times 0 minus 3, or negative 3. Okay. And it just suffices for me to find another value of x different from the first one and show that the function has the same value. This time I get negative 2 squared plus 2 by 2 minus 3, and that's going to be negative 4 plus 4 minus 3, or negative 3. And there you go. So we actually showed that the function is not 1-to-1 again. 0 is different from 2, right? x1 different from x2. If you want, call it x1, x2. We just showed that for 2 different x values, but f at 0 turned out to be equal to f at 2, both be negative 3. The combination of those two means that f is not 1-to-1. Okay. Example of the ones that would be 1-to-1 is this one. You can see that it's impossible for two different x's to give you two different y values. And you can actually also show these algebraically also, by the way. Okay, let's take a look at number 18. In number 18, f of x is absolute value of x plus 1 minus absolute value of x. So again, I'm going to choose counterexample. So I'm going to let, for instance, x be 2. So when x is 2, f at 2 is going to be absolute value 2 plus 1 minus absolute value of 1. And that's going to make it absolute value of 3 minus 1, which is 2. Right? Now let's take a look at when x is, 5. F at 5 is equal to absolute value of 5 plus 1 minus absolute value of 5. That's 6 minus 5, or 1. Hold on, I said 2, but I put 1 in here. Sorry about that. That's going to be 2. And there is 1. That's actually better now. That's what I wanted. So there you go. We just showed that for two different x values, we got the same y values. Again, 2 does not equal to 5, but f at 2 equals f at 5 equal 1. So the combination of those two tells us f is not 1, 2, 1. Okay. And again, you can draw the graph of these and do your horizontal line test to see that indeed whether they are or they aren't 1 to 1. Let's take a look at another one. Okay, in exercises 24 and 26, we want to find the inverse function at a point at a for the function f and the real number a. Okay, so again, we want to find the inverse at 2 here. So number 24. The problem is actually, what is f inverse at 2? Okay, now for these, we don't have to actually find the inverse. For some of these, we haven't even talked about the inverse trig functions. So how are we going to do this? So all numbers 21 through 26, for all of these we're going to use inspection. By inspection we're going to do that. So f inverse at 2 is what? So remember now, with respect to the inverse function, we have -2 and question mark. This is on the inverse. So when you translate this into f, that means question mark comma -2, right? So again, we want to know the answer to question mark, right? So by inspection, what I'm thinking is this: for what x values will the function take on a value of 2? Well, one way for this to be 2 is if tangent turns out to be 0, doesn't it? It's because if tangent is 0, I have 0 plus 2 and I get my 2 that way. How can tangent be 0? Well, several points, but we're restricted between -1 and 1, right? So between -1 and 1, I'm gonna say choose x to be 0. That's inside -1 to 1. So when you do that, then f at 0 is going to be 2 plus tangent of 0, because 0 times pi over 2 stays 0. And that's 2. There you go. So it turns out that x must be 2, and that actually translates into the y component of the inverse. Remember, when you switch the x and y, we're switching the domain and range of a function and its inverse. So if x is 0 for f, then it would be the same for y for the inverse at that same point. Therefore, the inverse at 2 is going to have to be 0. Again, by switching the role of x, y. That's why. Let's take a look at 26. Same thing by inspection. So in number 26, this time A is 1. Again, we want to know what is the F inverse at 1, right? That's what we want to know. Therefore, we're looking at, with respect to the inverse, let me write it. We want to know 1 comma question mark. Now that means with respect to the function, we have to do for what x will the function be 1, this being the function. So now for this one, and x has to be greater than 3/4 in this case. So greater than 3/4, let's choose 1. I don't know, I'm gonna let x be 1, a number that will work hopefully. So f at 1 is going to be 1/2 plus square root of 1 minus 3/4, and 1 minus 3/4 is 1/4. Square root of 1/4 is 1/2. 1/2 plus 1/2 is 1. Perfect. So f at 1 gave me 1. Remember, this is a guessed value. This, maybe I use a different color for that. Okay, this is what we guessed. We want to get these ones to be the same. So let's say if I guess, for instance, 2, I wouldn't get a 1. So I just got lucky that my first guess worked. Anyhow, now with respect to the function, therefore, point 1, 1 is on the function. When we switch or swap the x and the y, we still get 1. So for this one, this is on f, and then again when you swap, you get, maybe I use different colors here. There you go. Let me use a red color here. When we, and for this one, let me use a purple. And now when we swap them, this is how it turns out to be, 1 comma 1. Okay, this is on the inverse function, the point on the inverse function. Okay, so there we have exercise number 26. Let me grab a couple more. Okay, so here's our next set of examples. In exercise 47 to 54, let g be the inverse function. Show the point AB is on the graph of f, and then find g prime, that is, evaluate the inverse function at b. That's what we want to do. Okay, so first, to show that a point is on the graph, we need to show that when x is whatever is given, you plug it in, you get the y that's given. So here, let's take a look at f of x. F of x is given by x plus 1 divided by 2x minus 1. The point is 1, 2. So if I do f at 1, I should get 2. Plug in a 1, 1 plus 1 divided by 2 times 1 minus 1. That's 2 over 1, or 2. And there you go. So that means this is part A. So the point is actually a valid point. It's on the graph of the function. Now remember, for the inverse function, you switch the x and the y. This is the xy for the function. When we look at the inverse function, actually the point's going to be 2, 1, right? This is going to be the xy of the inverse function because we switch them, right? And the part B says find g prime at b. So we want to find g prime at, this is a and b. Do we want to find g prime at 2? There you go. That would be b, which is the y of the function, would be the x of the inverse function, right? And that's what we want to do. We want to do g prime, means evaluate g prime for its own x, which happens to be a 2 now. So we're going to use that theorem that we had, that we can find the derivative of the inverse using the reciprocal of derivative of the function composition of f prime evaluated at g of x. Oh, I'll put that down when time comes. Okay, first of all, I need to find f prime. Okay, so f prime x, that's standard. We're going to use quotient rule, right? Square the denominator, repeat the denominator, minus derivative of the numerator minus numerator times the derivative of the denominator. So this will make it 2x minus 1 minus 2x minus 2 divided by 2x minus 1 squared. And we have the simplified version, which is negative 3 divided by 2x minus 1 squared. So that's just the derivative. Now we're going to do the theorem that we had. So g prime at b is going to be 1 over f prime at g of 2 in this case. Okay, so that's going to be 1 over f prime, and g of 2 is 1, right? Because we were given the point. G of 2 is 1. So I'm just going to put 1 here, f prime at 1. And notice we didn't even find the inverse of the function, right? We know f. I did not find its inverse. If I don't know its inverse, how can I know its derivative, right? That is the derivative of the inverse, and that's what we're doing. We're doing derivative of the inverse without even knowing the derivative of the inverse. So this way we're just using all along, we're using f and f prime. We just take advantage of the given point. Now if we were not given a point, then we would have to probably just write it in general form. But anyhow, this is good. So I'm just going to plug into here. That's going to be 1 over f prime at 1 would be negative 3 divided by 2 times 1 minus 1 squared. And this is going to be 2 times 1 is 1 minus 1 is 1. 1 squared is 1. So the denominator is just negative 3. The answer is negative 1/3. Write it this way. So we were able to find the slope of the tangent at 2. On the inverse function, it's going to be negative 1/3. And there you have that. Very interesting, useful theorem. Let's do number 54. This time the function is 1 over square root of x squared plus 1. Okay. And for x greater than or equal to 0, and we want 1.1 comma root 2 over 2. Okay, and again for number 54, first to verify that that's a valid point on the graph of this function, I'm going to do f at 1. It's going to be 1 over square root of 1 squared plus 1, which is 1 over root 2. Rationalize the denominator, we get root 2 over 2. So that is indeed a good point. Now with respect to the inverse function, f inverse of x, which we call g of x, with respect to that, the point becomes root 2 over 2 comma 1, right? So we actually have a point on the graph of the inverse, but we want to find, this is what the question wants us to do, we want to find the derivative g prime at square root of 2 over 2. That's what we want to find, right? So let's move on to part B. In part B, we actually want to find the derivative f prime of x. And to do this one, I'm just going to write it as x squared plus 1 to negative 1/2. We want to find the derivative of that. So that's going to be negative 1/2 x squared plus 1, 2. Negative 1/2 plus 1 is negative 3/2. Negative 1/2 minus 1 is negative 3/2. Then chain rule, derivative of the inside. The 2 and the half, those 2's cross out. So this is going to be negative of x divided by the binomial to a negative exponent, which I can write as x squared plus 1 to a positive exponent 3/2 in the denominator. Okay. Now, what do we need next? Next we have to do, oh, okay, this is f prime. Okay, cool. Now we need to find g prime at root 2 over 2, right? That's what the intent was. So let's do that. So g prime at root 2 over 2 is going to be 1 over f prime. See that? This theorem relates the derivative of the inverse to derivative of the function, evaluated at the inverse function at root 2 over 2, right? Now, g at root 2 over 2, again, we have that information in the beginning. G at root 2 over 2 is 1. So I'm just going to put 1 over f prime at 1. True? And actually now we use f prime in our work. So that's 1 over f prime at 1 means negative 1 over 1 squared plus 1 to 3/2. And this becomes, we'll put negative in front of the fraction line. Invert and multiply the denominator. 1 squared plus 1 is 2. Invert and multiply. So I get 2 to 3/2, right? 2 to 3/2. And 2 to 3/2 is the square root of 2 cubed. True? That's negative square root of 2 cubed. So like root 2 times root 2 times root 2. Right? The first pair give you 2. So the answer is negative 2 rad 2. And that's what we wanted. Okay, so we're able again to find the slope of a tangent at the point, that's what g prime is, right? The derivative is the slope of a tangent at root 2 over 2 to the inverse function without even knowing what the inverse function is. And there you have it. So hopefully this helped you understand the ideas of this section. There's one more exercise I was going to look at. This one, number 60. So I'm going to copy that, bring it down, and then take a look at it. Okay, in exercise number 60, the problem reads, suppose the function f is 1 to 1 and twice differentiable on an open interval from a to b. Now, twice differentiable, that means the second derivative exists. If you want to take the second derivative, we could. That's what twice differentiable means. The second derivative exists. Let g be the inverse function of f. Show that g double prime, now that would be again the second derivative of the inverse function, is given by that expression, provided the denominator is not 0. Okay, so let's see how we're going to do this. I'm going to begin by first look at part A, then we address part B separately. In part A, remember our theorem said g prime of x is 1 over f prime of g of x, that composition. So that's given, which we can actually write this for the sake of what we want to do next as the denominator to a negative exponent, right? Now let's take the second derivative, g double prime x, in this form. So using the power rule, right, we're going to get negative of f prime of g of x, right, to a negative 2. And then chain rule times the derivative of the inside, right, the derivative of the inside. And derivative of the inside, the derivative of f prime would be f double prime of whatever, right? And then because again inside, in this expression, inside is g of x, then we have to use chain rule. That makes it g prime x, right? Now remember, g prime x itself is that fraction. So next step, we can actually tidy up this. F double prime gx, and let's see, F double, that's fine, we'll keep that one. I see. So F double prime gx, I'm going to write that as negative. Here's the numerator, F double prime g of x. Now g prime x again is 1. This is 1 over f prime g of x. And when I rewrite this expression, rewrite it, I get f prime gx. I'm moving it to the denominator. That to second power, it multiplies by g prime x times f prime of g of x. True? That's times gx because 1 goes in the numerator, that goes in the denominator. So hopefully you're able to follow this. Now that I have that, look in the denominator, we have same factors. So the denominator is in fact cubed of f prime g of x quantity to the third power, right? And the numerator is going to be f double prime of g of x. And that's what we wanted to show. Yeah, that's exactly what we wanted to show. Okay, now in part B, using the result of part A, show that if f is increasing on the open interval, if the function is increasing on the open interval from a to b, and the graph of f is concave upward, so it's increasing concave upward, right? If the function is increasing and concave upwards, it's gonna look like this, right? Then the graph of g is concave downward. Remember, this is the graph of f, so the graph of g would be actually this way. That's what we want to show. G is concave downward. Okay, so let's see for part B. Remember, f was increasing concave upward, right? We want to say that implies that g is concave downward. Okay, so for this one, well, f is increasing, right? So because f is increasing, f prime is going to be positive, right? What we're doing is just simple. We're looking at the components of this function, okay? Because remember, to discuss concavity, we look at the second derivative, right? So that's what in effect we're doing. Here, this is used for concavity, right? The second derivative test, remember that one we had for concavity. If we show that this is always negative, that means over the entire domain, then the second derivative negative over the entire domain, that means the graph of the inverse is going to be concave downward. That's where we're heading with this. So first of all, again, f prime is positive since f is increasing. We were told that, right? We were told that. Increasing on that open interval from a to b. Okay. Now, the graph of f is concave upward, right? We were told that. F double prime will be positive since f is concave upward. Again, both of those were given, but we're looking at the consequences of those given information. So they're upward. Again, on that same interval from a to b. So in part A now, right, in part A, therefore we see that g double prime is going to be less than 0 on interval from A to B, right? And again, we just showed the numerator, right? Let me write that. F double prime g of x, right? This is positive, and f prime of g of x is positive also, right? The components of the second derivative are both positive. And negative in front, that means g double prime is always negative, right? And that's what we wanted to show. So g double prime less than 0 on A to B, and that implies the graph of g, right, the inverse, is concave downward. That's of course over that open interval from A to B. Okay, so there you have it. Interesting observation. All right, now with that we are done with this section and with this lecture.